Okay.
All right, let's get started.
Yeah, good evening, everybody. Thank you for coming. We're members of the Peninsula Economic Society. First, I'd like to introduce Maria Cordell, who's our VP of the Peninsula Economic Society. She has a few words for us. And then after that, I'd like to introduce our guest speaker, whom I think you're going to enjoy quite a bit.
Yeah, so we're the Peninsula Astronomical Society, easy for me to say. Anyone who's new here for the first time today? Oh, great, welcome. Appreciate having you here. We run meetings about every other month right now with invited speakers and usually a range of really interesting topics, including tonight's topic. And we also run Foothill Observatory, which is on Foothill campus, and have that open every Friday night, every clear Friday night from 9 to 11 for observing, and also on Saturday mornings from 10 to 12 for solar observing. So the club is a pretty active group of astronomy fans of all ages and abilities, and we love sharing information and having an opportunity to meet in person at these meetings and so forth. And we're active at pastro.org, pastro.org, and also on Meetup. You can find us there. So I'm very excited about tonight's speaker. She and I were in undergraduate physics at Georgia Tech some years ago. In fact, we were president and vice president with the Society of Physics students. Mm-hmm. So, and studied some astrophysics together. So she's sorry for the pun, but she's a stellar person and astronomer, and I'm super excited to have her here.
Yeah, and I would encourage everybody to go visit the Foothill Observatory every Friday evening from 9 to 11, as well as Saturday mornings from 10 to 12 for solar observations of the sun. The views are amazing, and the stuff you can see is really quite good. It's free, open to the public. There's no charge for parking. And if you feel so inclined, I would also encourage everybody to join the club. There's a lot of benefits, in particular, if you ever want loaner scopes, yep. Talk to Ms. Cordell over here, and she'll arrange it. But you have to join the club. Okay, so with that, again, thank you for coming. I'd like to introduce the speaker, Professor McSwain. Received her PhD in astronomy in 2004 from Georgia State University, and had a very interesting dissertation title. So it's a little technical for me, but I really am looking forward to angle. It's about the evolution of massive stars, the BE star, and microquasar phenomena. Then she went on to hold an NSF, National Science Foundation, Astronomy and Astrophysics postdoctoral fellowship at Yale University.
Can you hear me? Somehow y'all have been muted. I can't hear you anymore.
Okay, can you hear me now?
Yes,
Okay,
yes. It got muted sometime during the introduction. So if you're ready for me to start, I will. But I just wanted to make sure.
okay, go ahead and share and
Okay.
if I need to change anything.
Yeah, it should be good.
Okay. Okay. Are y'all all set?
Yep, if we can hear you, we can see the slides. We're good.
It's a little loud.
Okay. Perfect. Perfect.
Um,
Um, Great. So it's a pleasure to be here to talk to you tonight. I'm sitting here in Bethlehem, Pennsylvania, where it's about 10 o'clock at night. So excuse me if I yawn a little bit. It's been a long day. Um, but I am really thankful to Maria for inviting me to speak tonight. As she said, we were old college buddies at Georgia Tech, and I remember taking our first stellar astrophysics class with her. I won't say what year, but it's been a little while.
Good.
And I kept going with it all the way through my PhD. And so I'm here to tell you tonight about a little project I've been working on with one of my undergraduates currently. Um, and the clever title was entirely his idea. Brandon Schweers is a undergraduate astrophysics major working with me right now. And he's the one who's done most of the work on this lately. The project kind of got started off a couple of years ago with my undergrad, Chris Aviles-Bramer, who's since graduated and gone on to grad school himself. But I'm really grateful to both of those students for putting in so much work on this. We're taking advantage of data mostly from the European Space Agency's Gaia mission, and we're using a lot of Python open source code, especially the AstroPy package and the GalPy package for galactic astronomy analysis. So I'm really grateful to all those teams for all the hard work that they have put into assembling the data and open source code that is useful for us. Um, so just to introduce what I'm working on a little bit, we are studying hot young stars in the Milky Way, and the Milky Way galaxy is a spiral galaxy, much like this one. This is M74, and it's kind of a good analog to the Milky Way in the spiral structure and the overall structure of the galaxy. You can see clearly defined spiral arms with young hot stars that kind of give the blue tinge to the arms in many places. And the red fuzzy bits in the spiral arms are star forming regions where young stars are currently being born. And the blue haze right in front of these star forming regions are the newly exposed emerging young stars. And these are all being born in the disk of the spiral galaxy. In fact, the disk of a spiral galaxy like the Milky Way or M71 or NGC 891, as you can see here, these disks are rather thin, and the diameter of the galaxy might be quite large, but the disk is rather thin in height. So so most of the stars, the most of the population of the entire galaxy is confined to this disk structure. And so it's pretty rare to find young stars that are not in the disk. But the reason for my project here is that there are about 100 young hot stars in the Milky Way that have been known for several decades, in fact, but they're found well above the plane of the galaxy. So instead of remaining with their compatriots in the plane, you find them at pretty high distances above the plane. And since these are young hot stars, their youthfulness suggests that they must have traveled a vast distance in a short amount of time in order to get to their current location, because there's really little to no star formation happening at large heights above the galactic plane. And so So the objective of our project is to figure out how and when they got there, and where did they come from, and just to try to figure out the history of these stars a little bit better. So star formation is taking place in the disk of spiral galaxies, much like this one. And these images of various spiral galaxies highlight in bright, ultraviolet light in this case, just where the star formation hotspots are. And you can see that it's very clustered in the plane of the galaxies. Each one of these little, bright zones probably represents a new cluster of stars forming. Yeah, probably several thousands or maybe even 10,000 stars that will soon emerge as a new open cluster in the spiral arms of these various galaxies. And so once the open cluster emerges, the young newly formed stars will blow out any dust and gas that remains in the environment, and then you will see a dense grouping of, several thousands of stars in most cases emerge. And generally, an open cluster like this has thousands of stars of the same age, of the same composition, because they formed out of the same cloud of gas. They're all at the same distance. And so open clusters like this represent a wonderful opportunity to study stellar evolution in a group of stars that have been co-evolving with fewer variables than you might otherwise have, just because you have this large population of stars with the same composition and the same age and the same distance. So a lot of the unknowns kind of fall out, and it becomes much easier to compare the relative differences between different stars. But the cluster environment is very chaotic. So when you assemble thousands of stars in a tightly packed environment, the gravitational in-body dynamics is rather crazy, and stars can get flung out of the dynamical environment all the time. And I'll see if I can replay this simulation here. This is just an in-body simulation with only 100 members, just to get the idea of the chaotic motions involved. But you can see several stars that appear to be flung out of this simulated cluster, and some of which might reach a large distance and turn around and come back in, only to get slingshotted back out. And so, it's the gravitational interactions in a dense open cluster can be very chaotic and fling out plenty of stars. And the denser the cluster, the more likely it is to happen. So a dense cluster like NGC 3293 here, for example, this is probably a location for, probably the source for many ejected stars. And so when we see stars that have been flung out of the galaxy at rather large distances from the galactic plane, we get suspicious. They must have been flung out from open clusters like NGC 3293, and it has companion clusters in the disk of the galaxy. And so my students and I have been using new data sets from the Gaia space mission, and using new Python packages with state-of-the-art Milky Way models to be able to predict just how the stars got to where they are and figure out where they came from. And so we are using, with the kinematic data from Gaia allows us to measure the three-dimensional velocities of all the stars in the clusters. This is all the kinematic data for the members of NGC 3293, for example. And so we know their positions in space, and we know their velocities. So it gives us kind of a six-dimensional set of information to trace them backwards. 3 dimensions in positions and 3 dimensions in velocity space. And we have similar data for the stars that are found above the plane. And so with their positions and velocities, we can trace them both back in time using a little bit of first-year physics, for example. Knowing the current position and velocity, And using a model of the Milky Way's gravitational force, we can measure the acceleration at each point, trace it back some small step in time and going back some small distance, to see what was its last position of velocity. Okay, trace it backwards. What was its position of velocity before that, and then before that, and before that. And so ultimately we can trace these ejected stars back in time and see when they would have come out of the disk. We do the same thing for the open clusters because they're moving through the galaxy too. So wherever they were when they ejected stars in the past, they have since moved too. So we want to trace both the stars and the clusters back in time and basically see where did they cross paths. And that gives us an indication of the time and place where an ejection might have happened. And so these are some of the results that we have found. For the cluster NGC 3293, which I'm using as a blue dot, the blue dot is its current location in the Milky Way disk. And this graph represents a polar representation of the Milky Way disk. So the galactic center is over here, and actually I forget where the solar system is, but that's not really that important. But this cluster is currently at this relative position, and the high latitude young star is, at least on this polar plot, doesn't appear to be very far away. But when I use a radial cutaway and plot the radial distance from the galactic center down here and the height above the plane of the galaxy, you can see that this cluster remains, nicely tucked in at height about 0 above the plane. But this star is found about 3,000 parsecs below the galactic plane. So that's quite a long distance. And so these trajectories appear to cross at a moment probably about 5 million years ago. And so this is a candidate for a parent cluster for this star, EC 23169 minus 2235. It's quite a phone number to remember. And honestly, I don't remember them. And so we have run tests like this for about 100 stars that we know have been ejected from the disk of the galaxy. And we just ran them against about 1,400 known open clusters in the plane of the galaxy. So it's a pretty large sample. And we got quite a few hits on, potential trajectory crossings. This is another example with the star EC 03462 minus 5813. And it seems to have crossed paths with the cluster Hog 18 just a few million years ago, maybe about 2.5, 3 million years ago in this case. So in the polar plot, you can see the polar plot kind of suggests that they may have crossed paths twice, but actually I think the most recent crossing time is the one to go with, simply because the other crossing doesn't actually match in height with the galaxy's disk. So this looks to be like the best moment of intersection when the cluster could potentially have ejected a star and sent it off flying down below the disk. And this is a third example with the cluster Berkeley 25 and the star HIP 115729. Again, this is a nice clear-cut example of a trajectory crossing. And so this is another great candidate for a stellar ejection event. And this is all fine and dandy. We have about 31 examples like this where stars trajectories match with open clusters. But that's not enough information to be able to really pinpoint, did the star actually come out of that cluster? So we did some further analysis using the HR diagrams for the cluster and the high latitude stars to see if the star's other properties match its companions in that potential birth cluster. So in an HR diagram, which is also called a color magnitude diagram, the horizontal axis is plotting basically the color of the star. The bluer stars are over here on the left, and redder stars are over here on the right. The main sequence of the cluster is visible as a nice diagonal line that runs from the upper left to the lower right. And these stars on the upper left are the hot O and B type stars, the very young stars. They're very blue in color, and they're very bright. They have bright absolute magnitudes, indicating a very bright intrinsic luminosity. So, so this particular high latitude young B star fits in very nicely with the other trends seen from this open cluster. So this is an excellent candidate for being a potential match. So I would say that we have pretty high confidence that the star EC 23169 probably could have realistically been ejected from NGC 3293. And NGC 3293 is such a dense cluster that this is a very realistic matchup. But other clusters, not so much. Like the cluster Hog 18, you can see a main sequence here. You can see the same similar main sequence running from the upper left to the lower right, but this is a much more sparse cluster. This cluster only seems to have a few dozen members left. And maybe it's been dissolving over time, which is why it could have ejected the star EC03462. But it's not as convincing a case because a sparse cluster doesn't have quite as much of the chaotic dynamics as a very dense cluster does. And so I would say that this is a maybe on the origin of this high latitude B star. And then another third example, the cluster Berkeley 25, has a main sequence that's much fainter. This indicates that Berkeley 25 is a far more evolved cluster where there's no more young hot stars left in this cluster at all. So if this young hot star did get ejected from Berkeley 25, it would have had to happen probably more than a billion years ago, and this young hot star wouldn't be so young and hot anymore. It would have evolved away from its current position as a young hot star on the HR diagram. And so the youthfulness of this star does not mesh well with the age of the cluster that's indicated by this color magnitude diagram. And so this is definitely a case where I would say this is not a real association. So this star could not have come from Berkeley 25. And so we've been running this matching algorithm for about 100 stars, and these are all hot young stars found, well above or below the galactic plane, and a preliminary matching finds potential homes for almost 30 of them. So roughly a third of the sample, which I think is pretty good given all the uncertainties and distance and everything. So there's a lot of uncertainty in these models as well. We find that 19 of those stars that have matching trajectories, at least 19 of those stars have trajectories that seem to match at least 2 or more clusters. And one of these potential matches even could have come from 9 potentially different open clusters, which is a little absurd. So there's 9 potential parents for this one star. Obviously, it couldn't have come from 9 separate places. And so we're currently working to use the color magnitude diagrams and density information about the potential parents clusters to refine these matches and say with more confidence which one we think it came out from. When we include the HR diagram analysis, it reduces our tentative matching list to 16 stars matched to parent clusters. We still get a couple of duplicates, but it's a lot fewer and it's a lot easier to start narrowing down, potential paternity in these cases. And so we're working now. Brandon has been fitting fitting the density distribution of these clusters to get a really solid measurement of the core density in all of the clusters in our, all the 1,400 clusters in our sample, so that we can look at those core densities and identify the clusters with the highest density and the most potential for ejecting stars from the heart of the cluster. And so we are getting ready to take this project to the American in January. And so we're really excited to finish it up and hopefully get it published soon after that. So anyway, I appreciate you being here tonight, and thank you for hearing about our results. I'd be glad to take questions and hear any discussion you might have about it.
Yeah, well, thank you so much, Professor McSwain. We got a couple of hands raised. I forgot who came first. Either way, okay.
I just,
Go
the
ahead.
last thing she said, she's gonna present at where, have faded out.
Oh, the audience is asking, a member of the audience is asking, you're presenting where? And
It's the American Astronomical Society meeting in January. It's the annual meeting of the of our professional society. We hold it every January in different cities around the country, and so we're going to be in New Orleans this January.
and that's strictly for professional astronomers?
I mean, not strictly. There are sometimes amateur astronomers and other visitors who come to these. It tends to be professional though. Yeah.
Okay. We're wondering if we could listen to you again, if you present, you can, you'd have
I wish they have declared that this meeting is in person only, and there's not going to be any remote access. So I apologize.
all right. And we had another question from the audience. Yes, go ahead.
If these are chaotic, how can you use Newtonian mechanics and calculations to project where they're going? It seems to me that it's you lose your ability to do this, find out the trajectories once the orbits become chaotic.
Okay, so in case you didn't hear it, I'll try and repeat the question.
Okay.
So these are chaotic orbits, and how does Newtonian physics apply to the prediction of the trajectories of these stars?
Right. Right. Sure. In the well, I decided to cancel my screen sharing here. So it's certainly within an open cluster like this, it is a chaotic environment, and there is no hope of retrieving the actual orbits of any individual star in that local, tight, chaotic group. But when a star is flung out from that and is at a large distance, then the motion is much more Newtonian because it's not feeling the close in-body effects of many companions at a large distance from the cluster. It's as if all of the mass of the cluster is concentrated at the cluster's center of mass, and that's a very long way away. So it becomes manageable. So ultimately, we're never going to know exactly, was it ejected from the upper left quadrant of the cluster or the lower right? We're never going to know that. But what we can know is just from the diameter of the cluster as it stands today and how the cluster is moving over time, we can see, does the trajectory of that ejected star match with the past trajectory of the cluster? And so especially because we're dealing with stars that have been flung high above or below the galactic plane, that eliminates a lot of the chaos too, just because the star's not flying through the galactic plane and interacting with all of the many stars and giant molecular clouds and spiral arms and all of the messy stuff that's in the disk of the galaxy. Above and below the plane, there's so little there that the forces, the force field is much smoother, and so can be integrated directly.
Yeah, we have a follow-up question, yes?
Right.
The Jackson star is still bound to the cluster? Are they in the magnetic gravitational field of the cluster?
Yeah, not anymore. That's the idea. They have been flung out of the cluster, so their speeds exceed the escape velocity of the cluster, and they are no longer bound to the cluster, but they are still bound to the galaxy. And so the gravitational field of the galaxy is dominating their acceleration from now on.
Okay, yeah, go ahead.
How big is the cluster? The average cluster?
Oh, yeah, okay, good question.
Yeah. These
Great.
clusters, they kind of vary in size, but we're calculating sizes of about anywhere from, a few parsecs, like 5 parsecs, up to 20 parsecs, I think, for some of the larger clusters. And the density of stars varies quite a bit as well. So, yeah, my student has been doing the fitting on the densities. And so I think he's going to finalize it next week, and we'll have some better numbers to go with on the densities.
Are you also asking how many stars or just the dimensions?
Dimensions.
The
The
dimensions.
dimensions, yeah. So there are a few parsecs across. Some of the core densities seem to be as high as like 20 or 30 stars per cubic parsec near the core of the cluster. And that drops off in the outskirts of the cluster, of course, but the core densities can be quite high.
Do you have another question? Yeah, go ahead.
I was wondering if you have actually matched the metallicities of the stars to their parent clusters.
Not yet. No, I would like to do that. Unfortunately, there's not a lot of metallicity data available for these. So being young hot stars, all of the metallicity surveys seem to be interested in like intermediate and low mass stars. So they don't get too many spectra of massive stars, unfortunately. And I think that's a terrible oversight. But so most of these stars have plenty of Gaia data available, but not spectroscopy and metallicities.
So if they're doing intermediate and low mass stars, maybe they can match the sun's original cluster by metallicity.
There are people who are looking for that. Yes. Yes.
Wow. Let me see, people who joined online, do we have questions as well? Are they
Perhaps,
muted?
I can't see it from here, unfortunately.
Okay, let me see if I
Yeah,
can.
I'll ask you a question, Jenny. Maybe you can tell us a little bit about your student. I'm curious if the student is an undergrad or a grad student.
Yeah, he's an undergrad. Brandon is a senior at Lehigh. He's planning to graduate this May, and I know he's looking for grad schools. So if you know anyone, yeah, he's been doing research with me for about a year now, and yeah, he's a bright student, and he's working really hard on this, and so yeah, what can I tell you? The conference in New Orleans is going to be his first conference, so we're really excited. I'm actually taking a large group of undergrads from Lehigh to this meeting. Brandon's working with me on this project, and I've got a student, Kevin, who's working with me on a really random project that involves a medieval manuscript on astronomy that's in our library. So we're doing some dating and location analysis on that. And let's see. Jacqueline is coming to the meeting, but she did her research at Villanova this past summer, but she's one of our Lehigh students coming. Oh, Kate is coming with me. She's working on massive stars in the Cassiopeia constellation. And finally, Nick is another undergrad. He does not work with me, but he's working on asteroids with another professor. But he's joining our team for the big trip, big hurrah in New Orleans. So we're really excited to have a pretty good showing from Lehigh going this year.
Great.
I
So
see a question from
Yeah, we
JT.
have a, yeah, go ahead. There was one from Rick Rogers, who's sort of following up to the Methodicity. Has there been any attempt at spectral analysis to see how those match between cluster and ejected stars? I think this is similar to.
Yeah, yeah. So I know that there's spectra exist for these stars because I know that they were taken a couple of decades ago and they've been published. But I don't believe anybody ever measured metallicities for them. And so it would probably take a little bit of work to dig out through the observatory archives and see if I could find those spectra. Have not done that yet, but some spectra exist. I don't know what the quality is, and I don't know if we could get metallicities from them, but yeah.
Okay. Are people, let's see,
Yeah.
is anybody muted that wants to speak?
JT has his hand up.
JT's.
Hi there. Sorry, thanks for, yeah, just a naive question. I'm surprised this hasn't been done before. Are there other people that have published similar types of surveys or other types of stars tracing their origin back, you know?
Oh, sure. Yeah. I mean, these are done occasionally. I'm aware of a paper that was published a few years ago that traced back some obscure low mass star and found that it passed within about 10,000 AUs of our sun just a few million years ago. And so it would have been a close enough passage that it probably disrupted some comets in our Oort cloud. And so stuff like this comes out every now and then. The Gaia mission, which launched in I think 2013, has been collecting just amazing data on the distances and proper motions of more than 1 billion stars in the galaxy. And so the Gaia data set is very new and very rich, and there is a lot of potential for exploring more than 1 billion stars in the galaxy to trace their kinematics back over time and do similar studies in cases where chaotic dynamics are not expected. So I'd say that you could probably look forward to seeing more tests like this one.
I have a particular question. I think I heard some numbers about 3,000 parsecs in 1,000,000 years.
Yeah. There's
How fast that is?
in
I was
per
trying to
second?
figure it out. It's like a fraction of the speed of light. It's quite maybe 1%, but it's still it's huge. Am I on?
Actually, I have not worked it out, so I couldn't tell you. This we traced the integration over 10 million years. And so in this particular example here, say Berkeley 25, the crossing point's at about the halfway point. And so so this particular example looks like it went 1,000 parsecs over the course of about 5 million years.
Wow.
So it is fast. And then this other example looks like got to its current location 3,000 parsecs below the disk in maybe 3 million years, and that is quite fast. So yeah, I'll have to work out what the kilometers per second is on that one.
There are runaway with these stars that have velocities like 300 kilometers per second, which is a substantial fraction of the speed of light for an astronomical object.
Yeah, but this is like almost 10 times faster. Yeah, it's crazy. Yeah, but
Although I don't know if it's in front of cluster would actually get that fast. Usually the ones that are like 300 kilometers per second, they're actually thrown out of binary systems.
Yeah, so there is another way to fling out stars actually, and as you mentioned, binary systems. If you have a pair of stars in a young binary, and one of them explodes as a supernova, then that supernova is going to basically remove a lot of mass from the system. And if it removes more than half of the total mass of the combined system, it will become unbound, and conservation of momentum dictates, the supernova flings off mass in one direction, and the former companion star is going to fly off in the opposite direction. And so that can also eject stars from clusters. These stars could have been ejected from supernova events also in the parent clusters. That's entirely possible. We really can't differentiate very well between a supernova ejection and a dynamical ejection from an open cluster.
One problem with that also is that when you have stars in a binary system, often the star that actually goes supernova, sometimes it expands into a red giant and then it dumps matter onto its companion star. And so
Sometimes,
the star thrown away actually sort of gets reset by all that injection of fresh hydrogen.
yeah,
so
that's
hard to match the HR diagrams of an ejected star with its parent cluster.
yeah. Yeah, that's also a possibility. I don't think I have any diagrams here, but some of the maybe matches that we found suggest that the ejected star could be a blue straggler, which could be an enriched binary, like you said. So that's a possibility.
That was the subject of my PhD thesis. So.
Oh, okay. Well, that explains.
30 years ago. So
We have one more another question from the audience. Yeah.
Remind me again, it's 4 light years. How long is the
Parsec is about 3 point something light years.
3.26 light years. Mm-hmm.
Thank you.
Mm-hmm.
Okay. Yeah. Factor 3 at least.
Yeah.
It's pretty impressive. And this is more of a curious question. You mentioned BE type star. What does that stand for?
Right. A BE star is a B spectral type star that has an emission disk surrounding its equator. So the BE indicates the emission.
Okay.
could that be a star that's like absorbed mass from its companion?
I'm sorry, I couldn't hear that very well.
Could that be like a star that's actually has actually accumulated mass from its companion, so there's like a disk around the star?
That is a common misconception about BE stars. They are not accreting mass from a companion. Actually, they might be post mass transfer systems and have accreted in the past, but in the case of a BE star, the emission disk is flung off of the star as a sort of decretion disk, some people call it. So the BE star is spinning so fast and probably also has pulsations happening at the surface. And so the combination of really fast rotation plus the waves are acting to help lift material off of the stellar equator and spread it out into a disk surrounding the star. So, yeah. These high latitude stars are not BE stars. I know that has been looked for, and they do not seem to have the emission disks in these cases. So, so we don't expect to find that, but certainly the open clusters I'm studying have plenty of BE stars. Like NGC 3293, I know has, I don't know, maybe a good 15 or 20 BE stars within the cluster still. So
Yeah.
Where again are the clusters? Are they in the galaxy?
yes, they are all in the plane of our galaxy. So I can't show you a nice picture of our galaxy because we don't have a camera that we can send out and look down on the galaxy. So I can show you this nice picture of a different galaxy that we are looking down upon. And so the open clusters are basically laid out in a similar way to the fuzzy red spots and the blue diffuse regions in the spiral arms here. So the diffuse blue regions are places where young stars have just recently emerged from their star forming regions. And then these diffuse red regions in the spiral arms are places where star formation is still ongoing. And the red emission here comes from hydrogen Balmer emission of basically excited hydrogen atoms in the molecular clouds, giving off that emission. And it's nebulous because there's a lot of dust and gas.
Are these clusters closer to the core of our galaxy than we are?
I'm sorry, what's that?
Are these clusters closer to the core of our galaxy than we are?
Oh, they vary in distance. Some are, some aren't. Yeah.
Do you see any clusters in the Milky Way like this?
Do we see any clusters in the Milky Way?
Our galaxy.
Oh, sure. Oh yeah, of course. All the clusters that I'm studying are part of the Milky Way. It's just hard to see the spiral layout clearly from our vantage point.
Well, come to our observatory tomorrow evening, and we'll show you a few open clusters.
Great, great, yeah. Yeah, this is a good time of year to see some open clusters in the galactic plane. Especially in the early evening when probably you could still see just after sunset, maybe maybe a little bit in Cygnus, Cassiopeia, stuff like that. So Cassiopeia is a really rich area for open clusters. Yeah.
What happens to open clusters? Do they continue to expand?
Will they continue to expand? Yes and no. Open clusters do tend to dissolve over time, and like members will trickle out slowly but surely. So, a cluster, like the one I've simulated here, might lose a handful of members slowly but surely over time. And as this cluster, passes through the spiral arms, it's going to be orbiting the plane of the Milky Way about every 20 million years or so. So the cluster is going to go as it passes around the galactic plane, it's going to be crossing spiral arms from time to time. It's going to be, probably passing near other clusters, near other giant molecular clouds. So it's going to experience a lot of gravitational perturbations along the way. And those gravitational interactions with neighboring objects in the galactic plane are gonna, help pull stars out, are gonna help disrupt the equilibrium of the cluster and just help the cluster slowly lose mass over time. And so open clusters are known to dissolve on timescales of about 200 or 300 million years. There are no open clusters known that are any older than 300 million years, I think. And very few older than, 100 to 200 million years because they just lose their integrity and dissolve. Since the sun is, of course, 4.5 billion years ago, our own parent cluster has long since dissolved. So it'll take quite a lot of work to match up the sun's companions, the sun's birth companions. The stars that I'm dealing with are a lot younger. And the fact that these youthful stars can't be any more than about 10 million years old really limits the number of possibilities. So that makes it an easier study.
Want to ask anybody online if you have questions. Again, feel free to raise your hand or unmute yourself. And happy to follow up. Yeah, go for it.
So after the stars run from the cluster, is it the same density, the same shade, and does it contain the same properties as the star from the original cluster?
So after the star is ejected from the cluster, yeah, the star retains all its original properties. It probably loses the chance to interact so much with other stars. And so it will continue evolving as a single star would, probably, unless it was thrown out as a binary, in which case the binary pair could be traveling across space together. But if it's thrown out as a binary, the higher mass of the binary means that it's going to have a lower velocity because the momentum of the pair is going to dictate a smaller velocity for the runaway star. And so I think these high latitude stars that I'm dealing with are all single stars now. So most likely they were ejected as single stars. And so they're just going to evolve as single stars would. They're not going to be accreting mass from a companion. They're not going to be enriched after they're ejected. They could have been enriched before they were ejected, so they would retain those properties. But since they were probably born with a group, the group is going to continue evolving, and the runaway star is continuing to evolve. And so they should be continuing to evolve at similar rates. And so you should be able to match the evolutionary status of both groups at whatever time in the future.
Yeah,
I imagine there's a lot of clusters. How do you select a cluster to study? Or you look for a runaway star or? how do you focus on it?
Yeah, so the clusters that we used in this study came from a catalog of all of the known open clusters in the Milky Way. And there's about 1,400 or so. These are just known groups. There's probably still additional clusters that are unknown, and certainly many clusters have been disrupted over time. So it's not a complete census of all of the open clusters in the history of the Milky Way, but it's the best list that we have. And the list of high latitude stars came from about the time I was doing my PhD. A colleague, John Martin, was doing his PhD at the University of Minnesota, and he actually studied this sample of about 90 some odd high latitude B stars for his dissertation. And so I know that he checked them to look for binarity and BE emission, but I don't think that detailed analysis of the metallicities was done before. So he has since left the field of astronomy, and so I know he's not working on these anymore, and so I can't really just call him up and get the data from him, because he probably doesn't have it sitting around anymore. But yeah, so I got the list and the idea for this project from our old talks way back when about these stars. 20 years ago, we didn't have the kind of incredible kinematic data that we have today. So he couldn't have traced them back in time with nearly the precision that we can do today. Gaia's precision is extraordinary, and it is really revolutionizing our understanding of the galaxy.
In the spiral galaxy photo that you put up a minute ago, I don't know how many clusters were in that. If there's 1,400 in the
Oh, sure. Oh, yeah. Yeah. Yeah, there's lots. There's lots. Any other questions or discussion?
Well, I was just wondering if you know how many clusters are in that galaxy.
Oh, and this one you're
what's
showing.
the average number in a galaxy.
M74.
No idea. To be honest, I have no idea. Given the angular resolution of this kind of image, I would say that, an individual red blob here is much, much larger in diameter than a typical cluster that we know of in the Milky Way. This is, this one red blob is probably a giant molecular cloud spanning, tens or hundreds of parsecs, because I don't think the angular resolution of this image is quite so good to be able to say that this is just one open cluster here. These illuminated red regions are enormous in diameter. So I don't think that I could pick out individual clusters on this image.
Well, if no further questions, I want to thank the Professor McSwain again. Thank you very much.
Thank you so much for having me, and all the great discussion. I really appreciate it.
Awesome. And I'll turn off the recording, but I don't know if it's probably past your bedtime by now, so And thank you. For those who in the audience who's gonna, any other questions you got for us, not to keep trying, or Professor Mike Swain, again, don't want to post too much on you, but.
Well, maybe one more question, this, with the incredibly precise Gaia data, and you're projecting backward in time, less than 10 billion years. So you get this trajectory that's heading toward the plane of the Milky Way. How accurate is that trajectory? Is it, you have to say, well, is it a trajectory that's so precise that it actually hits in a certain quadrant of the
yeah.
Is it
The errors in the trajectory are probably very large. One of the things that I have my student doing this coming week is to for each of the potential matches, run a handful of additional trajectories to consider the measured error bars on these distances and positional information. And he's already shown me some preliminary results on the error analysis, and they're pretty high. They're pretty high, genuinely. So I think what we'll be able to say is that, we could probably say with confidence that, there's maybe a 25% chance of a trajectory crossing, or a 75% chance of trajectory crossing. What we're hoping to be able to quote some kind of probability that these realistically happened. So yeah, the errors are high, and we're still continuing to work on that too.
Thank you.
Well, thank you very much again, Professor Mike Swain, and thank you.
Thank you so much for having me. It's been a
Thank
pleasure.
you.
All right. Good night. Enjoy your observing tomorrow.
Have a good night.
You too. Good to see you, Maria.
Me too. We'll talk soon.
Great. Good night.
Bye. Bye.